accurate. And this one video shows that why the tunable resistant Hall sensing can enhance the detection of small particles, because you see when the so you see when control the structure of the nanopore, you see the same particles creating more blockade signal, which create which is detected like even smaller particles. And the general measurement procedure following these 5 steps. Basically, we can measure size and concentration at the same time, or size and zeta potential at the same time. For size and concentration, we need to wet the nanopore, because when we get this one, it's totally dry. We need to use our wetting solution to wet the nanopore, and then to let it become suitable for measurement in solution. And the coating. Coating is we using a coating powder to make a coating solution. Because this one is made of TPU plastic, it may have some non-specific bonding to proton stuff. So we use the coating solutions to coat the nanopore surface and to prevent the non-specific bonding of the proton stuff to stick to the nanopore. The reason why we need to prevent the non-specific bonding, if proton attached to the nanopore, which will influence the baseline signal. You remember the previous one, need the RMS signal more than that. If too much proton stick to the membranes, it will rise the RMS signals, which means the noise very high. And after wetting, coating is optional. Sometimes it's very pure UVs don't need the coating, so just let it pass, because there's not much protein in it. That's the reason we use the combination of the QUV columns and the system, because after QUV, over 99% of contaminated protein is removed. For example, sometimes if some people have a plasma sample, we know plasma, but body plasma have lots of proteins, right? By using this one, they remove most of the protein. So all downstream analysis also requires very pure UV, so otherwise it will be influenced by those proteins. And after wetting and coating, so we will first analyze the calibration standards under different pressure. And then after that one, so we can analyze your samples under the same situation, same pressure, structure, voltage. After that one, so we export the data and then to our analyze software. For zeta potential, it's the same. We need to wet the nanopore and then coat the nanopore if needed, and then just follow the instrument guideline. So the instrument have 2 modes. One is the guided mode, which will have each instructions on the screen. So you just follow this. And the other one is advanced mode, which is all manual. The experienced user may just use the advanced mode because it operates much faster. So you can do as you like. For the guided mode, because since it teach you how to do each step, it takes a slightly longer time. And this one, for the zeta potential, we also analyze the calibration particle first under 4 different conditions, and then analyze the sample, and last step is data analyze. It is need to mention here, so between each step, because in the nanopore there are different solutions, you need to clean the nanopore. It's very easy, so just clean by DI water. And we mentioned here, so when you do, that's strange. Sorry. For the system, we need to do multiple pressure calibration, because why? Because for single measurement, we assuming the particle rate is 0 at pressure 0, but each particle has their surface charge. Under certain voltage, it can go through the nanopore due to its surface charge. That's why one pressure calibration is not that accurate. Only if your particle is nearly neutral or below, around the zeta potential below 10 millivolts, so the surface charge is lower. We know that if there's no pressure, so ideally, so the particle won't pass through the nanopore with no pressure pushing it. But because it has the surface charge, under the voltage, it will go through the nanopoles because of the electric force. So, but by this one, it's a single pressure measurement, it will treat it at a zero pressure, means zero particle rate. That's not true. That's why we need at least 2 pressure measurements. And the most, here, so we need to emphasize, because the JEV, the method also, guideline will also emphasize, when you're reporting a particle concentration, you need to include the range. For example, you can, because that is because each technology is different, because their measuring range is different. For example, when you're reporting your EV, you need to say, oh, from 50 to 200 nanometers, so my particle concentration is this. Take this one, for example, we say that from 17 to 180 nanometers, for example, concentration is 89 particles per mil. And this one is a video of how the system analyzes the particles. It's measures the samples automatically under 3 different pressure. For it, this one doesn't mean only nanopore block the issue, but usually you will come across like this issue because if your sample have very large particle, which will block the nanopore. And this one is the basic data analysis. We know that we run the same sample under 3 different pressure. You can see the particle rate. The higher the pressure, which means it's pushing the particle passing through the nanopore quicker, so the higher the flow rate. It's also used as a QC to check whether your measurement is good or not. You see this one is like a P8, P4, P2, which means P8 pressure, the particle rate should be higher than P4, and then should be higher than P2. And then when we report the concentration here, and then here the histogram report the concentration. On the left bottom, you can actually see it is individual particle information. This is control the focus. Yeah, you can see each particle's diameter and its relative information is here. And then on the right side is the your measurement. For example, each dot is 1 particle. You measure, so it depends on how many particles you want to measure. Usually we suggest from 250 to 500 particles, which is like a statistical significance. So that's why makes the TRPS unique. So TRPS reports each particle information, not like the optical method. It just give you some average numbers. And why TRPS is more accurate than others? There's lots of papers. This is one, for example. This paper is published on JEV, I think, several years ago. It mentioned that you can compare different technologies. You see that NTA, the accuracy is within 60% of its accurate number. TRPS is within 10%. Nano FCM is within 25%. Why? That's it, because TRPS is most accurate. Because TRPS analyzes single particles. If the sample, for example, is very complex, EV sample, yes, it is. For example, this is a 4-mode sample, which means it has 4 peaks, 4 groups of particles in the same group. You can see TRPS can distinguish each of the group. You can see the particle is from 50 nanometer to 350 nanometers. While NTA is just to give you a raw estimation of the 3 peaks, but it's artificial because it actually is 4 peaks. It gives you artificial peaks here because this one cannot distinguish these 2 peaks. For nano FCM, so we need to admit it's very accurate at the lower side. But the example has slightly larger particles, for example, above 150 nanometers, it will underestimate it. The DRS, we don't use DRS because DRS is just single angle like scanning. So currently no people using this one for GV studies. Also suggest my method guidelines don't use this one.